All right, ladies and gentlemen, boys and girls, here we go. So we're going to look through this problem real quick, get you information on sections C and D, and you guys will figure out real quickly. C and D I think it's them explaining a little bit of the things they already know, but you'll figure that as we go. So this is where we ended the last class on last Thursday, talking about an object on an incline. They use the example of this book sitting on an angle of 35 degrees. You draw the free body diagram, and if you notice, you have the force of the table. We'll now call that F then. And then we just added the force due to friction going up and then force due to gravity on the book. Now, if you notice, the force due to friction and the force on the table, we call F then, are all in the correct angle planes. So they're in the X and Y and what we want to do. Right now, we have to change force due to gravity. You guys have had practice with that. You separate force due to gravity in the X and force due to gravity in the Y. This is them doing that. And look, there's your force in N, force in X, and 22 newtons. Sine and cosine, the very long-winded version of how to do that. And look at below. Hey, look. Force due to gravity is 13 newtons. Force due to gravity in X. Actually, that's a typo. I didn't see that till just now. That's annoying. I'll try and fix that. But again, force due to gravity in X, force due to gravity in the Y. Y is equal to 0 because it's not coming off the table or going into the table. Force in the X is 2 newtons going down the incline, so you can find the net force. Now this is important because this is where we kind of stopped. You found the net force. And what that means is you now have a net force. You can use that going forward. And this is where sections C and D pick up. So talk about inertia, one of Newton's laws. Basically, the bigger the mass, the more inertia it has. Inertia, in its definition right there, is basically the tendency of an object to resist changing in its motion. So example, the best one I like is talking about football players. A football player running down the field. I'm like 198 pounds. I don't have a lot of inertia to move that football or stop that football player. Ain't gonna happen. I mean, I could go straight at him and he could go straight at me and we're going that way, whatever way he was going. That being said, he's got more inertia than I do. First law, law of inertia. Objects in motion will stay in motion until acted on by an outside force. So, mass, one of the best ones. This is a simple seatbelt example. Basically, it's got a large mass and it's a pin. And this is why, like when you go around a corner, some of these, this is a simple version which just tilts forward and backwards. But one of the ones you guys will have can vary its angle quite rapidly. And so even if you go around a curve, it can lock up your seatbelt. Kind of helpful depending on what you're driving. And I've seen you guys drive. It's crazy. So equilibrium, the net force on the object is 0. And we kind of talk about this real quickly in class. We'll say the force is equal to 0. The idea is if it's a net force is equal to 0, it's not speeding up or slowing down. Not that it is at 0, meaning it's not moving. Just meaning the net force is not causing a change in the current object, all right? So I'll let you guys read through that. If you want to stop it, you can. Cool, moving on. Section 3 is where we pick it up. You have the net force, mass times acceleration. Cool. Newton's third law. Two objects interact. Yeah, blah, 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 blah. For every action, there's an equal and opposite reaction. Okay? That's the easiest part. And we will get to right there. Difference in mass and weight, magnitude and normal force. We've already talked about this in class. If you were paying attention, you've got it. Gravitational force, F of G, towards the center of the Earth. It is scalar. It is called weight. Weight changes with location because the mass of the planet you're on will change. So, force due to gravity is just the mass times acceleration due to gravity, 9.81. Moving on. Mass to weight. Don't know why that slide's not showing up, but mass to weight, simple version, mass doesn't change, weight does. That's the biggest thing. Mass doesn't change, weight does. Normal force. F of n is coming out of that board, it's what keeps the board from sagging. The version they like to say, normal force is not always opposite direction of gravity. Correct. It is the restorative force. That's why we like that term, restorative force or normal force. Again, static friction, objects not moving, objects are at rest. Kinetic friction, objects are moving. Kinetic friction is always less, static is always more. All right. Free body diagrams, I'm not going to go through. Coefficient of friction, there's our two equations, another version of it. You'll see this often in your textbook, Fs max. Just because static friction is the highest point, that's why it's your max. So, coefficients of friction, you don't have to write this down, you can, but we'll always reference this page in your book. So, and then sample problem, if you want to stop, I'm going to stop it here. You can write this down, you can pause the video, try and find the acceleration of the box. It's a good one to do. If not, we'll pick up with this on Thursday. All right, have a good day.